All right, so today we are going to take a look at a few more examples of logarithm and exponential problems, a little more complicated, but we're just using all the properties that we've gone over last week. I believe, yeah, I think we're going to wrap it up with exponential and logarithms this week. We'll see how tomorrow and Wednesday go. Okay. So here I have a few more examples. All right, so let's go through these. So the first one I have here is an exponential, but we have some stuff on the outside. All right, so remember, anytime that you have a variable in your exponent, okay, to solve that, there's two steps, or there's two ways. You're looking for a common base, and if you don't have the common base, then you have to use logarithms. But before we can do anything with this, we have to remove what's on the outside. Okay, so again, I'm going to say it. Anytime we're dealing with equations, you work from the outside in to isolate your variable. So looking at our equation here, 2 times 3 to the 2x minus 5 minus 4 equals 11. The first thing we want to remove here, or not remove, but move over to the right side of our equation, would be the negative 4. Okay, you could divide by 2 first, but be careful. When we multiply or divide, it has to go to every part, right? That has to be distributed. So if you divided by 2, you'd have to divide this by 2 and this by 2. Right? So I don't want to deal with any unnecessary fractions. So the first thing I'm going to get rid of is minus 4. Right? So we're going to add 4 to both sides. So on the right side, I get 15. That's a 15. And on the left side, we remove that 4, and we just have 2 times 3 to the 2x minus 5. So again, we need to do one more thing before we can look for a common base or anything with the exponent. I have to get rid of this 2 on the outside. Right? So we're multiplying by 2, so I'm going to divide both sides by 2. So that's not going to get us a nice number, so we're going to leave that as 15 over 2. Okay. For now, that's enough. Again, I don't want to deal with decimals. This is a nice decimal, right? This gives us 7.5, a nice decimal. But we're going to avoid that if we can. Okay, so now that I have on the left side, we have the exponential part alone by itself. The first one we look is, can I get my right side into the same base? Well, 15 over 2 is 7.5. There's no way that 7.5 is a multiple of 3. Okay, 15, yeah, but it would have to be a 9 up here, so there's nothing that we can do. Okay, so because we don't have a shared base, right, we have to do the inverse of our exponentials, which was our logarithms. So because my base here is 3, I'm going to choose a log base 3. So I'm just going to write everything out. Right, so all I did was I added a log base 3 on both sides. Okay, whatever I had originally goes in the parentheses. So on our left side, the log base 3 and the 3 cancel each other out. They don't technically cancel, right? We use our properties. I bring this out to the front, and then log base 3 of 3 is 1. So we're just left with 2x minus 5. Now over here, this is just a number, okay? because this is a number inside here. So log base 3 of 15 halves is just going to get us some number. But like I said before, we want to be as accurate as possible. So I don't want to round. I don't want to cut off any decimals. So for the rest of this problem, for now, I'm going to leave this as log base 3 of 15 halves. Okay? We're going to save this until the end. But for now, it's going to stay log base 3 of 15 over 2. So now on the left side, I just have a normal algebra problem. So we just go through the same steps to isolate the x. So I add 5 to both sides. Now, with this, okay, I'm just going to write log base 3 of 15 over 2 minus 5. Okay? And then our last step to get the x alone would be to divide by 2. So the accurate, exact answer, let me make this, put it down here. Oh, I'm sorry. This should be plus 5. Okay, my exact answer is log base 3 of 15 over 2 plus 5 divided by 2. Okay, and what I'm going to do is I'm going to put this in parentheses up here. Now, if they ask you for an exact answer, this is what you're going to give them. If they ask you to round to 3 decimal places, right, which is what I will tell you to do it when I tell you to do it. This is what you're going to plug in, okay? And you're going to plug it in order. So there's a lot of going on here. So actually, let me move this down. Okay, so real quick, I'm going to calculate this on this calculator, just so we have a reference number. So I'm going to have, okay, so again, if you're dealing with a graphing calculator, if you hit the math button, you have all these different options, and you can pick the log base, right? So you can enter log base 3. I'm going to type in now 7.5, but it's the same as 15 divided by 2. And I'm going to put this in parentheses. Plus 5, close parentheses, divide by 2. Now, doing this, okay, if I'm plugging this all in at once, I have to make sure I put those parentheses here. Otherwise, if I didn't have the parentheses, the calculator would do 5 divided by 2 and then add that to the log. And that's the incorrect order of operations. So I have to make sure to put the parentheses in my numerator to say that I'm doing that first. Okay, so here we get about 3.417. So I'm going to put that off to the side. 3.417. If you have to do this in a few other steps, if you can't do this log base 3 part, okay, you would have to do the change of base here. So you would have ln of 15 halves over ln of 3, and then you would have plus 5 over 2. Okay, this would get you the same thing there. Let me show you, though, what happens if we round here first. Okay, so say I had to calculate this, and I don't have this log here. So I'm going to do the change of base. I'm going to do the natural log of 15 over 2 divided by the natural log of 3. So I calculate that first. And even if I round to 3 decimal places, okay, I have 1.834. So now with this number, I'm going to add 5 and then divide by 2. And we get a pretty close approximation, okay, 3.147. All right, but that's because I used 3 decimal points here. Actually, no. That's because actually, let me do this. 1 point. So let's say I did 2. So 1.83. I'm going to add 5 and divide by 2. Okay, so if I just rounded from the beginning, okay, my answer is close, but it's off a little bit. Okay, the less decimal places you have, again, the less accurate you're going to be. Now, for our math class, you know, if you're off by 2 1/1000ths, it's not a huge deal, right? I can see if I'm grading your papers where you went wrong, and I can, you know, mark it accordingly. But if you're doing something important like measurements, you know, for a job, and you're off by 1/1000th of an inch, that could have some big repercussions. Okay, you know, if this is for business, if you're dealing with somebody's money, okay, 3.417 million and 3.415 million, well, that you're missing out $2,000 there. Okay, so that's, you know, that could be a big difference for somebody. All right, so we want to be as accurate as possible. But again, since we rounded, all right, I put that squiggly line for approximate 3.417. Okay, any questions about that one, the exponential? All right, let's take a look at this second one. All right, so this one is a logarithmic problem. So again, there's 2 ways that we're going to approach this. One is if we have a logarithm on both sides and they have the same base, then we can just worry about the inside. Well, we have the same base, but there's 2 logarithms over here. Okay, I can't get rid of the logarithmic part because I have 2 terms on this left side. But we do have logarithmic properties where I can combine these. Okay, this is a minus. When we are subtracting 2 logarithms with the same base, then we can divide what's on the inside. So these 2 terms we can combine into a single log base 6 of 3x plus 14 over 5. And then on the right side, we didn't touch anything, so we're still going to have log base 6 of 2x. Okay, again, this is a number, but if I calculated what this was, you know, point something, that's not going to help me. If I move that over, then I'm still dealing with some weird things. Oh, excuse me. Okay, so now that we have a single log base 6 on the left and the right side, all right, technically we exponentiate both sides and they cancel each other out. But in reality, all we're doing is we're looking at what those values are. So we have 3x plus 14 over 5 equals 2x. And now we just go about normal algebra. Okay, so dealing with this is a little simpler. Okay, you don't have to worry about any logarithms in your answer. So you multiply both sides by 5. We subtract 3x from both sides. and we divide by 7. All right, any questions about that? Do I have enough time? No, we'll do that tomorrow. All right, let's do one more problem. All right, so here we have log of 5x plus log of x minus 1 equals 2. So this is the other instance in solving with logarithms. Because we don't have a logarithm on our right side. All right, so if I had a logarithm on the right side, then I could just worry about what's inside, right? We would combine and then just focus on what's in the parentheses. But over here, there is no logarithm. So first thing we'll do is we'll combine these. All right, so I'm adding two logarithms. So I'm going to be multiplying what's inside. So here I have to distribute this 5x to the x minus 1. So both of these, all right, again, addition means multiplication inside. So I'm going to have a single logarithm of 5x squared minus 5x. And that's going to equal 2. We didn't touch the right side. Now that I have a single logarithm over here, okay, in order to get these x's by ourselves, here we have to exponentiate. I don't see a base, so that tells me that my base is going to be 10. We have that invisible 10 there. So I raise both sides, and I have a base of 10. Okay, those will cancel out. I'm left with 5x squared minus 5x. On the right side, 10 squared is 100. Now, we got to be careful. I have two x values. So even if I separated, if I factored out an x, I'd still have, I'd have 5x times x minus 1. So here, we're going to set up a quadratic by subtracting 100 from both sides. All right, I'm going to move that 100 over to the left. So now I have a quadratic equation. They all have a factor of 5, so I'm going to pull that out to make things easier for us. Right. Now I can use, the quadratic formula, but this is factorable. So two numbers that multiply to 20 would be 5 and 4. They add up to negative x. One of them has to be positive, one of them has to be negative. We'll make the 5 negative since that's negative. Right, and we solve for x. So this first term, the 5, we set equal to 0. That's not true. We can forget about it. X minus 5 equals 0 gives us x equals 5. X plus 4 equals 0. X equals negative 4. All right, we have two solutions. But remember, for logarithms, x has to be greater than 0, or what we plug in has to be greater than 0. So if I plug in 5, well, I get 25 and I get 4, so that's no problem. If I plug in negative 4, I get negative 20 and negative 5 here. We cannot do that. Okay, so I think I mentioned it last week, But here we have an extraneous solution. Okay, so we only have one answer, x equals 5. X equals -4 is a solution, but when we go back to plug it in, it doesn't work. All right, so you do have to be careful with that when we're dealing with logarithms. Okay, again, our domain x has to be greater than 0. Okay, and also be careful, it cannot equal 0. So if for whatever reason, if I got +1 as an answer and I plug that in here, I can't take the log of 0, right? Because no power, gets me a 0 as an answer. Okay, any questions?